Hey everyone, and welcome to our physics project. I'm Parker Moon, and this is Nikki Gratz.
Hello, everybody.
And today we're going to be looking at the difference in velocities and the difference in energies of a tennis ball that was thrown in the air and then is bouncing.
All right, guys, before we come to our analysis, we're going to look at our video first. And so basically, we're going to throw a ball and let it bounce on the table, and then it bounces on the floor and goes right into the trash can. We're going to look at the velocities and energies before and after the first and second bounce.
For our first analysis, we wanted to look at the ball at this point, right as it's leaving his hand, and examine what forces and what velocity is on the ball at this point before it's even in flight. So here we're going to look at the forces on the ball right as it's leaving Nikki's hand. So here is a representation of the ball. And if you look over here on the left, this black line here represents where the table is. The rest of the line up to the blue mark represents the initial height of the ball as it's leaving Nikki's hand. And as you can see, the potential energy at this point is going to be maximum. The kinetic energy, since it has no downward or forward motion at this point, is going to be zero. So now if we look at what forces are on the ball, we're going to see that in the x direction, we have the force of the throw. And we also have the drag force facing the opposite direction. And this equals out to this force here in black in the rightwards direction. And if we look in the y direction, we're going to see the force of gravity. And these two forces will equal out to form a force here in blue, a force of F at an angle. Okay, so here we're going to look at the forces on the ball just before it hits the table. As you can see over here on the left, indicated by this blue mark, the ball is just above the table. So at this point, the kinetic energy of the ball is going to be maximum. And we can calculate this kinetic energy by looking at the difference in the potential energy at the max point, which is where the ball was released, and the min point right before it hits the table. So now let's examine the forces that are acting on the ball at this point. Of course, we have the force in the x direction and the drag force pulling in the other direction from that, which equals out to that black arrow there moving to the right. Then we have the force of gravity pulling the ball down towards the ground, which gives us a total force in the direction in which the ball is moving in blue there. All right, so here we have the graph of the y position of the tennis ball during its flight and subsequent bouncing. So what we can see here is that we can examine the difference between the start potential energy and the final potential energy. And it's pretty obvious to see here that from the initial release of the ball to the maximum height of its first bounce, the ball loses some energy. And we can calculate about how much energy it's going to lose by calculating the difference in potential energy and then putting the final potential energy over the start potential energy. This gives us a coefficient of restitution, which can also be calculated by using velocity 2 over velocity 1. So for this, we calculated the coefficient of restitution to be 0.753, and this basically means that the ball has about 75% of the energy it did at its initial release.
All right, so we look at the forces on the ball at the first bounce, and we see that the ball hits the table at an angle B with the force F. The resulting force is pointed upwards with the same angle B, and it's 0.753 of the original force. We call that force F1. So we found out that the coefficient of restitution for a tennis ball is about 0.87 till 0.94. So this coefficient of restitution varies from material to material. So the table has a different material than the court. So this is why our coefficient of restitution is about 0.753. So since the resulting force is pointed upwards, we're gonna reach about 75% of the maximum potential energy. And we look at the forces at this point again, and again we have the force in the x direction and the drag force, which is pointing in the opposite direction. And these two equal out to the force in the x direction. And then we have the force of gravity, and the resulting force between those is F with an angle.
So here we have the ball just before it hits the ground. And if you look over here on the left, you can see the potential energy and the kinetic energy at the peak of its previous height. And here we have the ball represented by this blue line here, and we can see that potential energy and potential energy is zero, and then kinetic energy is going to be maximum. We can calculate our kinetic energy by looking at the differences in potential energy. So now let's get into the energies that are acting on the ball. So first we have F1 coming down at an angle. The angle at which the ball hits the ground forms angle B with the ground. Then we have F1 times 0.753. This is what we would expect the force to be here, since this is what we calculated our coefficient of restitution to be. But in actuality, that's not what we found it to be, and we'll get into that a little bit more on the next slide. So here again, we have the graph of the y position of the tennis ball, and now we're going to look at the coefficient of restitution for the second bounce. So once again, we find the PE initial and the PE final, and we find our delta PE, and we plug it into this formula, put PE final over PE initial, and we calculated our coefficient of restitution to be 0.8 over 1.28, or 0.625. And that's not good because it doesn't equal our previous coefficient of restitution, which we had assumed that it would. Some reasons for this different coefficient of restitution is the different surface that the ball is bouncing on, as well as tracking mistakes, which will be explained in the next slide.
Alright, so these tracking mistakes mean that we give the software wrong information, and this software calculates other graphs based on this information. So we see here an x position graph and the x velocity graph, and the x position graph should be a straight line. However, we see here some peaks. For example, at t equals 2.3, we see that there are minor mistakes, which result into huge mistakes when we look at the x velocity graph at t equals 2.3. Same with t equals 3.3, we see that the graph changes direction, and this results into a bigger mistake with t equals 3.3 at the x velocity graph. So the x velocity graph should be a straight line at like about 1.6. The reason is because the x velocity doesn't change overall. The same thing happens with the y position versus the y velocity graph. As we see here, there are tiny mistakes at t equals 2.7 in the y position graph. These mistakes result into a major mistakes at the same t equals 2.7 seconds. Same happens for t equals 3.6 at the y position graph, which result into major mistakes in the y velocity graph as well.
Hey guys, we hope you all enjoyed watching our project, and we just wanted to leave you with one last piece of information. What is the only thing that you serve but don't eat? A tennis ball.